Good evening and welcome to our final Sibzi technical seminar for 2020. Thank you very much for coming along. Tonight's session is H2X, Hydraulic Design and Calculation Tools by Jonathan Moosdell. Just before commencing, if we can go to the next slide, please. I'd just like to acknowledge traditional owners of the land on which I stand today, Wurundjeri people, and also acknowledge the traditional owners of country throughout Australia and recognise their continuing connection to land, waters and culture. We pay our respects to the elders past, present and emerging. Next slide, please. A few items on Sibzi, and one of the key ones is the knowledge portal. As building services professional, everything we do and operate is built on knowledge. Whatever the building project you're working on, there is an essential online tool that you'll need, and that is the Sibzi Knowledge Portal. This online resource hosts hundreds of engineering and building services publications, including all the latest and up-to-date Sibzi guidelines and standards. And this guidance is actually free to members and just one of the many benefits of membership. So if you're not already a member, apply online and take advantage of this invaluable resource. Next slide. Volunteers. We're always on the lookout for volunteers, both Victoria, New South Wales, Queensland, Sibzi-wide. Volunteers are the foundation of the Sibzi community. There are so many ways and reasons to get involved, from personal growth, networking, and shaping the industry. Find out more at sibzi.org/get involved or email Sibzi ANZ Business Development Manager Sharon Pestonji. Tonight's session is a very exciting session, and it's the overview of H2X, which is a hydraulic design and calculation tool created and launched in Australia this year. Whilst it offers an alternative method of designing water, gas and sewer systems, our speaker Jonathan will discuss the journey of developing H2X, including potential drawbacks of traditional design methods, which prompted the creation of H2X, and also the engineering challenges faced throughout the development of this software. Jonathan is a senior hydraulic engineer at Warren Smith & Partners in Sydney and one of the founders of H2X. He is also chairman of the Water Demand Committee, which is in the process of completing the first update to the Australian standards pipe sizing since 1945, which is a pretty significant history. We have Q&A at the end of the session, so please feel free to type in your questions as we go through, and Jonathan will pick them up at the end. And a recording of this webinar will be made available in the week after the event at the Sibzi website for webinars. And with that, I'll hand over to Jonathan.
Cool. Yeah, thank you for the introduction, Sean. It was really nice. And yeah, thanks for giving me the opportunity to speak tonight. So yeah, Sean kind of covered it. We're just going to be talking through the journey of why and how a couple of friends and myself decided to create H2X, which is software that aims to improve the building services industry as a whole. And yeah, going to be talking about the problem that we wanted to help fix, our idea on how we can contribute to fixing it, and then just some of the technical difficulties that we've come across along the way. So it really all started when I was just on the bus to work one day and I was reading a construction magazine and was very shocked to read that 32% of construction defects come from the design phase of a project. And I just thought, wow, that's really high. And normally don't have much sympathy for contractors, but on this occasion, I just really sympathized and thought it must be very frustrating for them. And what really put it into perspective for me as an engineer was thinking, if 32% of issues in our design came from things that we relied upon to be correct, such as the Australian standards, it would just be pretty inconceivable to think that well, could even be a possibility and it would be allowed to continue that way. So obviously the number can't go down to 0% because that's just not reality and it's not the industry that we're in, but it really should be a lot less. We should be at least trying to get it down to be a lot less. So this just led me to questioning why is this such a high number and like what is the underlying cause? So from my experience, really boiled down to two main reasons. Firstly is that the current design process that we follow it's just become very time constrained over time. And every project now just seems to be in such a rush. And then secondly, the design process has become very iterative. So as an engineer, I feel like I'm forever chasing my tail, just trying to keep up with the architectural changes and also just general project changes as well. So just to summarize it a bit simpler, it seems that there's been technological advances in most of the areas of the construction industry. And this has been making our job as an engineer harder. And unfortunately, as an engineer, this is something that's not within our control. It's on the more with the project managers and the clients. But what is in our control is how we react to it as engineers. And we all know that it just hasn't really advanced at all in recent years. So just for those of you that don't know, I'm just going to talk through the traditional process that is followed when we do designs and calculations. And it obviously starts off when we receive the architectural drawing. We then have to manually draw out the system, measure all the different pipes that we've drawn, and then we need to quantify all the different components. And then we manually transfer them back into spreadsheets. And there isn't just one spreadsheet, there's multiple spreadsheets for different parts of the system that we want to calculate. And then once we get the results, we then need to transfer the results back onto the design. So as a graduate, I used to enjoy the process. It was quite fun to learn the calculations and try and make things work. But I suppose as time constraints got a bit more, the novelty soon wore off. And just from doing the process multiple times, just realized there was 5 key issues with the process that we followed that just meant it was just outdated compared to the rest of the process that we're dealing with from the project. So the first one's pretty obvious, but it's very time consuming. It's also very tedious. So measuring pipes and counting fixtures is definitely not too much fun. And then because it's so tedious, there's a huge risk of human error. So we're triple handling information from the design or from the drawing to a spreadsheet, and then we're taking the results from the spreadsheet and putting it back onto the design. And then QA is also very difficult with this process. So if you're trying to correlate results that you might see on numbers that you might see on a spreadsheet and compare that to the numbers or the sizes that you see on a drawing is very difficult. And on a large building, it's probably nearly impossible. And lastly, redesigning is problematic. So when we receive the new architectural layouts, it's very difficult to make a change to the spreadsheets because you can easily get lost, especially again on a really large building. If you change something on one level, it's really hard to track what changes on the levels below and the levels above. So just with all this was burning in the back of my mind, and the weeks went by and I was carrying on doing my job, I could just start piecing together where I thought these problems were coming from, or at least how the improvements could be made to make our lives easier. And again, there was 5 key things that stood out. And the first one is that we should be able to automate the tedious parts. So if we're able to not have to measure pipes or count fixtures, this would free us up to spend more time actually thinking like what is the best design possible to suit a specific project. And then again, by automating the tedious parts, it would significantly reduce the possibility of human error with all the information that's being transferred. And then it was also apparent that to improve the process, it's imperative that the user would be able to easily make design changes. So when they get the new architectural designs, they can modify it to suit really easily. And then of course, it needs to be easy to perform a review. So whether that's an internal review from your colleague, or if you're sending it external to a peer review consultant. And then lots of information gets lost between the designer and the drafter. So we needed to bridge that gap as well. So at this point, it became pretty clear that we needed to replace the traditional process, and we needed to replace it with a powerful and easy to use alternative, which obviously sounds really good, but was it possible? So that was the next step to finding that out. So our concept at this stage was to just replicate the traditional process that we follow, but do it on the cloud. So this would work by, if we update the architectural or upload the architectural drawing into a software and make it so it's to scale, that would then mean that when a user draws pipes, the length is automatically measured. And then when we connect to the fixture, that fixture would have properties like loading units. So it would increase the flow rate as all these components are tied together. And we'll see it now as well from a concept level. When we then connect the WC, all the flow rates would update upstream and downstream. And then the beauty of it is, once you could determine the flow rate, it's really a knock-on effect, because then we were able to size the pipes, which would be based on the maximum velocity parameter, which the user would select. And then from there, we could work out the pressure loss in the system. And then once we had all that designed, we're able to work out all the different calculations that form part of hot water return. And then lastly, we'd be able to calculate all the dead leg volumes and lengths. So that really covers off the introduction to the problem. And now just going to start talking about how we got into the details of building H2X, and then just some of the difficulties we had along the way. So just to summarize the introduction, from my point of view at least, it seemed like the existing hydraulic design process had become very outdated, especially when compared to the rest of the industry. They were starting to now use or utilize efficient technology, and we were being left behind. And then just to put a bit of timeline to all of this, so really had the problem, or became aware of it in 2018. And then June 2019 is when I started to really get serious about wanting to make a solution. And then that takes us to July 2019 as well, where the next step was really time to build a team. So luckily I had some good friends, so it didn't take as long to for the three of us to get going. But there's a clear hole in the team was that none of us knew how to code, and we didn't know anyone that knew how to code as well. And that was a pretty important part to get this off the ground. So just as with all good love stories, we took to the internet to find someone, and we just posted about our idea and what we were looking for. And really, we're looking for someone who's going to be excited by the opportunity. And as you can see by this message that we received, and received plenty of these, it was very difficult at first. Not many of them contained much excitement about the idea. But I think if you increase your surface area enough, you'll always find a bit of luck. And it just so happened for us that there was an ex-employee of Google and Microsoft who had competed in computer science world finals that wanted to, I suppose, give that up and join us in building pipe sizing software, which was really good. So from here, the next 4 months for us were really about going from an idea and creating what's called a minimum viable product. And that's not a term that I suppose most people are used to in the industry. What it is you just want to make something that is as minimal as possible, but has enough benefits to create value to the user. So you don't want to go too far ahead because you don't want to go down the wrong path, but also because you're putting pretty much your limited savings into this, you want to make it so that it's good enough that people will pay for it. And then from there, you can just continue to add to it, sorry. And it was only just when I was reviewing the slides earlier, I thought it looked a bit deceivingly easy. So just wanted to add this in, just to show there's a lot of ups and downs really at this part, but really, it was all worthwhile when we got the first customer in January this year. And within the first week, we got a lot of feedback, which is a really good sign. But it became pretty clear, as you can see from these responses from our three early adopters, that we'd focused too much on all the hydraulic features, and we'd missed some obvious things that we needed, such as an undo button. And we also had a user forgot their password, and we didn't have the functionality to reset it, so we just had to reset them up with a new account. But it's all part of the process, really. And the main thing was that customers were engaging with us. They were looking for a solution to all the problems that I had and I'd built a team telling people that there was such a problem. And then at this point, we just agreed that every dollar we'd get from customers, we're just going to reinvest back into the product and just make it better and better. And we're also fortunate enough along the way that we received a grant from the New South Wales government, which really helped us get going at the start of this year. So from all the features that we got requested, the most difficult one was definitely hot water return. So it's obviously very critical to a hydraulic product. And that's not just to the amount of variables that you can see on the screen here that contribute to the design. These are all not too hard for software to understand, but it's more where human judgment is exercised that it becomes really hard to recreate with software. So I'm just going to go through a few of the challenges that we had with building this feature. And the first one is, I'm not sure if you can see my mouse on the screen, but it's highlighted in yellow anyway, but the calculations need to be iterative to comply with the Australian standards. So it requests here that you combine the heat loss flow rate with the PSD, which effectively brings you to this flywheel really, which is once you've designed your system and you've done your calculations for the flow part of it, you then need to work out the heat loss for all the pipes, which then takes you to the next step, which is you got to add that heat loss to the peak flow rate. And then once you've done that, that usually means that some of the pipes in the system need to be upsized because the flow rates exceeded the maximum velocity. So that then brings you back to the step we were at before, which is because the pipes have upsized, there's more heat loss through the system. So you go through again, you do all the calculations, and then add the heat loss flow rate back onto the PSD. So the pipes that you've just upsized more than likely would not need to be upsized again, but the ones that didn't need to be upsized last time probably would need to be upsized. So that then brings you back to the first one, and around you go, and eventually it stops. Gets pretty confusing, but long story short, we figured this out. Another issue was that you need to make sure the pressure is balanced at all points in the system so that it circulates correctly. So I think it's common knowledge, you need to work out the heat loss flow rate and you need to work out the pressure loss at this heat loss flow rate to circulate the system. But what isn't common knowledge is that you actually need the pressure where all the return pipes join back together. You need the pressure to be equal for it to make sure the water doesn't take the path of least resistance. So an easy way to do it that you commonly see in the industry is that, just to talk through this example, you might have 420 kPa coming through this part of the circuit, and then you've got a balancing valve where you might lose 10 kPa, and then through the vertical part of the pipe you might also lose a little bit more. So that means that when these points interconnect here, they really want to be at the same pressure. But generally this one would have higher pressure, which in this example has 450 kPa. And if you only set this to lose 10 kPa for the balancing valve, that means you'd have 440 at this point. So that's a 60 kPa difference. So effectively what's going to happen in this case is the water is going to take the path of least resistance, which generally is this. And that's just going to mean the rest of the system is not going to circulate at the right temperature, which is non-compliant, and it's going to get you some complaints as well from the users. So we had to come up with a really complex algorithm that could really detect where all these points were interconnecting to each other. And then, I mean, it's pretty simple in hindsight, but what we had to do here is if we had 440 at this point and 380 here, the 60 kPa difference would need to be added on to the balancing valve, meaning that the pressure drop would be equal through here, and yeah, the system would circulate correctly. So again, we got over this one. And then just the last example that I just want to go through is it's doing all the calculations is one thing, but then if the system curve doesn't actually meet a pump curve almost exact, there's a good chance you're going to have a non-compliant system. So just using this as an example here, our system duty was 0.2 liters per second at 1 meter head pressure loss. And because that didn't quite sit on the first pump curve, or setting for the pump, it gets pushed up to the second setting, which, as you can see, it takes a bit of a trajectory. So this means now the flow rate is pretty much 0.3 liters per second. The pressure's increased as well, which isn't really a problem. But with this flow rate increasing, you've done all the right things in your design, but if you forget this one key step, your system is going to be non-compliant again, and it's also going to be at risk of failure from erosion, corrosion through high velocities. So as we can see here, going from 0.2 to 0.3 liters per second means that the velocity rises from a compliant 0.89 to a non-compliant 1.34. So this isn't something we wanted to just leave our users with to fix themselves. So it is it's not a well-known issue in the industry, but I suppose Grundfos are obviously aware of it because they get called out to site a lot. So they were more than happy to partner with us. And that means that we now have the Grundfos pumps in the software, and we've in the code, we've got the 3 different pump settings, which is pump setting 1, 2, and 3. And what we've been able to do is, instead of pushing the flow rate up, like in the first example, we just add additional pressure loss to the system, which is again through the balancing valve. And that means we can just rise directly, not have to upsize the pipe, not have non-compliant velocities, and we can sit perfectly on a pump curve so that system can circulate correctly. So again, it was quite a big challenge and a lot of work to get through, but came up with a really robust, good solution in the end. And then this is just to give an accurate representation of, I suppose, the feature designs and how it all works. So really the part I was involved in was the blue. So for me, there was a lot of downs on the process, as there was problem after problem that needs to be solved. But eventually got there. I figured out how the design or the user interface could work and how the calculations could work. And then at this point, you usually just pass it over to the developer and yeah, just wait to review it. But in this case, it was pretty much a straight no from the developer, and he just thought I was crazy. But we talked through it, and luckily he is very crazy. So he was able to get it done in the end. There was a lot of downs and even more downs in this case, but yeah, we eventually got there. So I just want to, just got a little video here, and it's only 30 seconds or so. I just want to show you how quick and easy it is, or I suppose what the outcome was for all this design challenge. So it's only a really small project, just so you can get a feel for it, a bite-sized section, but effectively all that's required to do the result, to do the designing calculations is you've got your hot water plant, and then effectively you're just drawing a polyline really that represents hot water pipes. And the main thing you've got to do is, as long as you've got a flow and a return that connect to the hot water plant, you've already picked your parameters like velocity, insulation thickness, and temperatures. So just by drawing the pipes or the lines that represents the pipes, and then you just need to add some nodes to the system. Let's pause. And the clever thing is, the software, and we'll go into it a little bit more in a few more slides, is detects problems. So this is instantly seeing that there's we're missing a balancing valve on the flow and return system. So if you'd missed it, it's pretty hard to send out a non-compliant design or an incorrect design. So it literally just come back into the design space, pick a balancing valve, and just put it on the system somewhere logical. And then we can just head back to the results. We can see instantly that not only was all the flow rates, return flow rates, pipe size, and pressures at the nodes being calculated, but it's automatically worked out the heat loss flow rate and worked out the pressure drop through the system, and then put us on the correct Grundfos pump type and which setting to be on. And like I was talking through before, there wasn't actually 24 kPa drop through the system, because we knew that if we didn't add the pressure loss to sit on the pump curve, it would be wrong. We've been able to add the pressure drop through this balancing valve. So we lose 22.5 kPa here, which gives us a total of nearly 25. So you've got your balancing valve kV values automatically done. You've got your circulating pump all sized. You've got all your pressures at your fixtures, and you've got all your return pipe work sized as well. So it's a really, it's turned out to be a really quick and easy solution where you don't even have to differentiate between flow and return. The software can pick that up for you. Cool. All right, and then next, I just want to show you a few more videos just to show you how over the course of this year, we have been able to benefit our users in the way that we originally set out to with those 5 key values. So in this video, I just want to show you how we might have a design that's already been done. So again, it's a very simple example, but as you can see, we've got all our pressures at the fixtures, pipes are sized, and hot water plant circulating is all sized. So now what we need to do, we just come back into the floor plan space, click to replace a PDF, which you can't see me do because the pop-up hasn't shown. But you can see here now, if I just pause, that the background has changed. So this block of toilets is gone, and we've got a new kitchen added here. So real quick and easy, you can just delete those fixtures that we don't need anymore. Modify your pipework layout to suit the new architectural layout. And then, yeah, we just got a new kitchen sink, so you can just quickly add that in, select that and connect it to the pipes that you want to connect it to. And then as quick as that, you can get your results again. So again, it's a very minor or small scale example, but if you think of this on like a 10-story building and you're making changes to level 5, it's really quick and easy to make a change to a certain level. You don't have to worry then about checking things on the levels below and the levels above. It's all done for you. Okay, and then the next slide, I just want to show you, this is what the PDF export looks like. And the aim of this is to help with the QA reviews. So again, whether it's internal or external. So first of all, you get a cover sheet that accompanies the export of the results. And this has all the project information auto-filled. And then it also has design parameters and flow system parameters as well. So before someone gets too much in the detail, they can just review it from a high level and just make sure they're happy that you're using the right standards, the right velocities, the right materials, and spur capacities, and a few other parameters. And the beauty of it is, if someone wasn't happy that you used a certain material or velocity, you don't have to redo your calculations. You just go back into the software, change the parameter, and everything updates instantly, and then you can just re-PDF and send it. So it's very flexible and easy if there is something that we want to change. But then when it actually comes to reviewing the results, so results are all specific to each component. So as you can see here, all this flow rate, height, and size is all specific to this cold water pipe, specific to this hot water pipe, and then again, specific to the fixture. And we provide design warnings as well. So for example, if you've got a really large building and you're playing around with the pump size or putting pressure reduction valves in places, it can be pretty easy to just forget to check a certain level and see how things turn out, which in the software is borderline impossible really, because you get these nice big yellow warnings. So in terms of these pipes, you can see here that we've exceeded the maximum or the safe working pressure of the pipe material. For the pressure reduction valve, we can see that we've the pressure step down ratio is more than two times of the target pressure, which manufacturers don't recommend. And then you can see here that there's too much pressure at the fixture. It exceeds 500 kPa, which again, manufacturers don't recommend. So it makes it kind of foolproof to a certain extent to get the right results. Okay, just this video as well is just to show you how easy it has been, how easy you can share once you've done your design and got your calculations, you automatically then have a markup for the drafter, which you can just share to them through a link. So it's really good because you send them a link like you do here, click on the link, and then what they get is this read-only version of the project. So the drafter is not able to then go in and change the design or move pipes around. But what they can do, similar to how Google Maps works, they can the further they zoom in, they can see all the information that they require, which could include pipe sizes, as well as the height of the pipe as well, which is very beneficial for if they're modeling in Revit. And as you can see here, some information that might not make it onto a 1:100 markup is some of these smaller segments of pipes and the sizes. But as we just saw, you can just zoom in and see everything that you need to. And they can also just flick around all the different levels and you just get a feel for everything. So feedback from customers has been very beneficial to keeping the design errors from the drafting down. Okay, and then just the last video, this one's just a little bit different. And I just wanted to say that I suppose along the way, customers have requested features from us to help them with other constraints in the day-to-day activities. And one of these is providing a cost or an overall budget to the QS, and also being able to assess value engineering options, which happens on most projects. So what we've got here is we've got the cost included in the software, which is all based on components from Rawlinson's or prices from Rawlinson's. And we can see overall we're at over $208,000. Oh, sorry, $2,083,000. We've got really high flow rates here because we're using the Australian standards. And just in the matter of 30 seconds, we can see that there were 150 pipes there. You can come in, change the project settings, and then instantly see that not only have the pipe sizes downsized from 150 to 65 as the flow rates have come down, the cost has also come down as well. So I think that's around $30,000 cost savings that you can feed into the client or the QS. And then you can even take it a step further and come back into the project settings and just change some of the parameters around the flow system. So you might want to up the velocity, which again shows that we've come down from a 150 pipe all the way down to a 40 mil pipe. And you can tell your client that you've saved them quite a bit of money. And then what's not shown in the example is as well that you can export bill of materials, which you can provide to the contractor. Cool. And then just to finish off, last slide, just understood that a lot of people here from mechanical and electrical backgrounds. So we are aiming to release a product in those disciplines next year, and the long-term aim is to become collaborative between the disciplines. But we just have last few items really to finish off on the plumbing version of the software, which you can see here, and one we're working on at the moment is exporting into Revit, which should be really good for the customers. But yeah, that really is everything. So yeah, I hope you guys enjoyed the brief story, and yeah, I'm happy to stick around to answer questions. And I've just put my email up here as well, because I'm always happy to speak to people. So yeah, please email me if there's any questions come up in the future, or yeah, just like to discuss anything. Cool. All right. There is a few Q&As. Sorry, I don't know if someone's going to...
Thanks very much, Jonathan. That was really good. Yeah, so if you can see the Q&A, if you want to start going through those.
Yeah, sure. Cool, yeah, so we got 4 questions so far, so I'll just read through those. First one is, what has been the feedback from customers? So yeah, customers of all, yeah, everyone that uses the software really loves it. So they're reporting huge time savings, increased quality, and then actually 20% of our customers have come through being recommended from existing customers, which has been really good. And yeah, they're all engaged. They're always asking us to add more features, which, so we've always got a healthy backlog, and yeah, that's been really good. And then I suppose kind of ties into the second question as well, which is like, what is done in other countries, and is this relatively transferable? So we've actually had users from 7 countries sign up, which all of our customers are mainly in Australia and New Zealand, and we do have plans to go overseas as well. Especially in the UK, we've started to get our first customers now. But yeah, there's been a big appetite for it, surprisingly, in India, because they generally don't design to standards. But the country, they now want to design to standards because they're having so many problems and they're trying to grow. And funnily enough, the engineers can't design. They don't know how to design. They just pick pipe sizes based on the last job, and I suppose put a pump in if it's a tall building. So there's been a lot of interest there. We just need to add a few things for them, and then yeah, US there's been interest, and then a few of the Middle Eastern countries as well. So yeah, it's definitely a global problem. It's not just something that Australia hasn't evolved over time. Next question is, how does this fit into the design phase with Revit? So yeah, this is quite it's a question that comes up quite often, because BIM, I suppose, is quite confusing of what the terminology is. But yeah, really Revit is for documenting once a design's finished. So really they go hand in hand, and that's why we want to export what's drawn in H2X into Revit. But effectively, it's a standalone, or it's a different part of the design phase. H2X is really good for designing and calculating and coming up with different options. And then it's really once those options have been finalized, that's when it can then be drafted in Revit and soon to be exported from H2X into Revit. And the last question is just, who certifies the design? So yeah, because we've similar to like Excel, it's obviously tailored to the industry, but it's very flexible. So we don't tell anyone what to design, like we've seen the warnings for minimum maximum pressures, that can all be overridden by the user. And like we also saw as well, you can change the velocities. So similar to Excel, you put in your own parameters, and for that reason we can't provide certification, because, and like one of the examples I showed there, we use the German standard, which obviously doesn't comply with the Australian standards. You can design to a really high velocity, and I suppose you could leave 10 kPa at a fixture with non-compliant, and yeah, that's not something that yeah, we'd be able to certify. So the onus is still very much on the engineer. We're just trying to make it easier for them to do the design and make it easier for their for the colleagues or the external peer review consultant to do the review. And then, sorry, yeah.
I was just going to say, there's another question that's come through on the chat. Would this software be applied to gas?
Yes, sorry, gas is already in there, so I didn't touch on that. I didn't want to talk too much about features. I just wanted to talk about benefits and how we're trying to improve the industry with the benefits. But yeah, what the software currently does water and gas. we have sewer coded, and we did release it for beta testing, and now we're just fixing a few bugs. So yeah, it's water, sewer, and gas, and soon to be stormwater. Cool. And then there is actually another question that's come through on the Q&A. So someone's asked the cost of the software. So it's been priced to provide 10 times the value of the cost. So in terms of like the overall cost savings for your average company over the year. So that works out to be $2,000 on an annual subscription. And that includes training. So detailed product demonstrations, and then training of the team, and then you get access to all the ongoing releases, which I mean you can see from this year we started off with a pretty minimal product, and now it's really robust and does lots of features. So yeah, that all comes included with the cost. Yeah, is there any other questions from anyone?
Seems to be a few questions coming through on cost. Oh, there's a technical one. How to deal with flush valves?
Okay, sorry, I'm just looking at these now. So, sorry, it can be applied to gas. Yeah, okay, so yeah, it is for sale. So sorry, I should have said with the cost as well. So yeah, it's $2,000 per license, and that gives you one account to log in on. But say if you've got a team of 5 people, everyone gets their own user account login, and the only limit is the amount of concurrent users. So you can all 5 people can have access for the price of 1 license. You just can't have 2 people in there at one time. So yeah, generally we sell 1 license per 2 engineers, because that works out where they're not really cutting each other off. But yeah, for 1 license you can have yeah, your whole team onboarded. And then you're dealing with WC flush valves. So yeah, you can override. So everything can be overridden as well. So whether it's a fixture or a pipe, so whether it's a WC, you don't have to have 1 loading unit or 0.1 liters per second. You can add a continuous flow and set it. So if you had cooling towers, it could be 6 liters per second. And if it's, yeah, even if it's a vacuum toilet and you might not want 1 loading unit, you can reduce that as well if you wanted to. So for WC flush valves, same thing. You can just stamp a WC and just override the properties to be what you want it to be. Hopefully that answers the question. But yeah, if it wasn't clear, let me know and I'll explain it again. I feel like I went around a little bit.
Well, that's really good, Jonathan. There's no other questions coming in. Probably just thank you, and also Jordan. Obviously, Jordan's involved in this process as well for sharing your experiences. It's been very much appreciated. And just with that, I'd just like to say that this is the last Sibzi event for 2020. So a big thank you to everyone who has supported us throughout this crazy year that has been 2020. And we certainly look forward to what's going to happen in 2021. Hopefully we'll get Jonathan back in and talk about the trials and tribulations as this software has been developed. And yeah, thank you very much for attending tonight, and stay safe, everybody.
Sure. Cool.
All right. Thank you.
Sean.